a group of n girls and n boys took part in a mathematical contest. It is known that each contestant solved at most 6 problems. Also, for each girl and each boy, at least one problem was solved by both of them. We have the following main problem. Prove that if n is equal to 21, then there was a problem which was solved by at least 3 girls and at least 3 boys. Also, show that if n is smaller than 21, then the previous assertion is not necessarily true. Our approach for finding a solution is to represent our data with the following table of size n+1. We insert the group of girls in the top row and the group of boys in the left column. We associate a different symbol to each different problem. If a symbol appears at some square x in our table, then this means that the corresponding boy and girl in the corresponding row and column which contain x solved the problem associated with that symbol. For example, the problem associated with the heart symbol was solved by the corresponding second boy and third girl in our table. And as can be seen, this problem was also solved by the last boy and the second last girl in our table. Our table of symbols must satisfy the following 3 conditions. First, observe that each square in our table is not empty, since we assumed that each boy and each girl solved a problem together. Secondly, our table has to satisfy the consistency condition, which means that if some symbol is found on 2 opposite corners of some rectangle, then this symbol must appear also at the 2 other corners of this rectangle. This is because, if the first corner corresponds to boy X and girl Y, and the second corner corresponds to boy Z and girl W, then, since the same symbol appears in these corners, then it follows that all of these 4 participants solved the same problem associated with that symbol. In particular, this implies that this problem was solved by boy X and girl W, and by boy Z and girl Y. This equivalently means that the symbol must appear in the other 2 opposite corners. Lastly, since each boy and each girl solved at most 6 problems, then in our table, each row and column must contain at most 6 different symbols. Let us now return to our main problem, and first prove that if n is smaller than 21, then we can construct a table of symbols, such that no problem is solved by 3 different girls and 3 different boys. It is enough to construct such table in case where n is equal to 20, since we can reduce the size of this table for the other cases. Let us now begin the construction of our table of size 20. First, we divide our table into 4 equal quadrants, as in the illustration. Let us insert 5 2x10 rectangles horizontally in the first quadrant, such that each rectangle has a different symbol. Let us do the same for the fourth quadrant. Let us now insert 5 2x10 rectangles vertically in the second quadrant, where each rectangle has a different symbol. Let us do the same for the third quadrant. Let us first check that our table is valid, that is, that it satisfies the 3 previously mentioned conditions. For the first condition, it is clear that each square in our table is not empty. For the second condition, Observe that if the same symbol appears in opposite corners of some rectangle T, then, since each of our 2x10 rectangles has a different symbol, then T must be contained in one of these rectangles. And thus T has also the same symbol in all of its squares, which implies, in particular, that its two other opposite corners have the same symbol as the original two opposite corners. Thus, the second condition is also satisfied. As for the third condition, if we consider a row in our table, then this row must intersect a horizontal 2x10 rectangle. Hence, this rectangle, with the same symbol, will occupy 10 squares. Our row will also intersect 5 vertical 2x10 rectangles with the same symbol, which will occupy another 10 squares. In summary, we have, at each row, exactly 6 symbols. The same can be proved for the columns in our table, and thus condition 3 is satisfied. Lastly, we need to show that no problem was solved by 3 different girls and 3 different boys. Equivalently, we need to show that no symbol appears in 3 different rows and 3 different columns. However, this is immediate, since by our construction, for each symbol, X, all its appearances must be inside one of our vertical, or horizontal, 2x10 rectangles. Then, if X is inside a horizontal rectangle, then it cannot appear in 3 different rows. Similarly, if X is inside a vertical rectangle, then it cannot appear in 3 different columns. Let us prove now that if n is equal to 21, and in case where our initial assumptions, with regard to the questions that were solved by the groups of girls and boys, are satisfied, then there must be a question which was solved by 3 different girls and 3 different boys. Equivalently, let us show that if we have a table of size 21, which satisfies the previously mentioned conditions, then there must be a symbol which appears in 3 different rows and 3 different columns. Our method for the proof is to assume that one can construct a table such that no symbol appears in 3 different rows and 3 different columns. And then, we need to obtain a contradiction. For this, let us divide our set of squares into 2 subsets, X and Y, where X is the subset of squares whose symbol appears in at least 3 rows, and Y is the subset of squares whose symbol appears in at most 2 rows. Observe that X and Y are disjoint sets, and their union is the set of all 441 squares in our table. Our goal now is to try to estimate the number of squares in each one of the subsets, X and Y. First, we claim that each row in our table cannot contain more than 10 squares from the set X. Indeed, let us take some row R in our table, and let us distinguish between the following 2 cases. If each of the symbols in R appears in at least 3 rows, then, since each of these symbols belongs to at most 2 columns, then each of them must appear at most twice in R. Since R has at most 6 different symbols, it follows that the number of occupied squares in R is at most 12, which is a contradiction, since all the squares in R are occupied, and R is of length 21. Hence, there exists at least one symbol in R which belongs to at most 2 different rows. As was explained previously, each symbol in R, which appears in at least 3 rows, also appears in at most 2 columns. Thus, since the number of symbols in R, which appear in at least 3 rows, is at most 5, it follows that the number of squares in R, which occupy a symbol, which appears in at least 3 rows, is at most 10. This equivalently means that R cannot contain more than 10 squares from the set X. Since this is true for every of the 21 rows, it follows that the set X contains at most 210 squares. In the exact same way, we can prove that each column in our table contains at most 10 squares from the set Y. And similarly to the previous case, this implies that the number of squares in the set Y is at most 210. Thus, the union of the sets X and Y contains at most 420 squares, which is a contradiction to the fact that it should contain all the 441 squares in our table. Hence, we arrive to a contradiction, which implies that at least one problem was solved by 3 different girls and 3 different boys. This proves our assertion, and thus our proof is finally complete.